The linear regression model for the problem we've been working on so far exists in this format. Y hat, and it's called hat because it's an estimating agent to distinguish it from Y actual, which is the data we collected from the experiment, equals beta sub 0, which is the overall mean, and you would have to go back to the very first table and get an average for all the data and the replicates. Beta sub 1 is the linear coefficient for factor A. Beta sub 2 is the linear coefficient for factor B. Beta sub 3 is the linear coefficient for C. Beta sub 4 is the linear coefficient for AB, so on and so forth. However, you must remember that in the ANOVA table, we found out that all the interaction factors, AB, AC, BC, and ABC, were not statistically significant. So we could scrap them from our linear model. So your linear model should look something like this, to where Y hat equals beta sub 0, the overall mean, plus beta sub 1, the factor A linear coefficient, times A. Now eventually to estimate, you will need to plug in values for A, B, and C. So for a run that has A at low, you plug in -1 for A. If B is at high, you plug in +1 for B. And let's say C is at low, so you plug in a -1 for C. Now for the overall mean, this would be the average of all the data and the replicates. So I'm going to scroll down here to show you the replicates here and highlight all the cells, close the parentheses, and that will be your overall mean. Your final regression model should look something like this. Y hat equals the overall mean plus the linear coefficient for factor A times A, which is 1.65 times A, plus 1.88 times B, minus 2.8 times C. Now it's minus because the linear coefficient is minus. So this should be your final regression model. Notice that we disregarded all the interaction factors